All right, so now we're looking at Chapter 2. We already did the sample problem 2.1 in the actual video for Chapter 2, and now we're going to do sample problem 2.2. You have the sheet, I gave it to you. We're going to look at the analysis of 84.2 grams of pitch blend. Which contains uranium. Okay? And it contains 71.4 grams of uranium. Okay? But it says oxygen is the other element. How many grams of uranium can be obtained from 102 grams of pitch blend? 102 kilograms, sorry, of pitch blend. First thing we have to know is that pitch blend obeys the law of conservation of constant composition. The amount of uranium in pitch blend should always be the same. So if I can establish the percentage of uranium in pitch blend, then I can go ahead and figure out how much is present here. So that's what my game plan is going to be first. I'm going to do the percent composition, or mass fraction, we can call it. I don't want to multiply by 100 of the uranium. So I need, ready, the mass of uranium. Now, if I wanted to find the oxygen in this one, I would just do the mass of oxygen on top, but I just want the uranium. Total mass of the compound on the bottom. Okay, so then we end up with 71.4 grams over 84.2 grams. And we'll do some math right here. We'll turn it on, clear, 71.4 divided by 84.2 equals 84.8, right? Sorry, let's try that again, yeah, or 0.848. And so this is consistent according to the law of constant composition. All pitch blend should be this much uranium. So if this is the amount of pitch blend I have, I just have to take the 102 kilograms and multiply it by 0.848. And that should give me the pitch blend. Oh, sorry. And it says it's 86.5. So that means 86.5 grams of uranium exists in kilograms of uranium exists in 102 kilograms of pitch blend. All right. Sample problem 2.3 we did together in class. Sorry, we did as part of the video. Sample problem 2.4. It deals with silicon, and we're going to deal with 3 different types of silicon, or atoms of silicon. We're going to call them 28, 29, 30. Now, these are what we call, we'll put it over here on the side, right, isotopes, which means same number of protons, different number of neutrons. And since in the atom, all of the mass is located in the center, that's where the protons and neutrons are, these are the same elements with different masses. So isotopes are the same elements with different masses. Okay, so in this problem, in sample 2.4, sorry, we want to determine the number of protons, neutrons, and electrons in these things. And some other things to point out, ready? We'll keep over here on this side. Atoms are when the positives equal the negatives, so no charge. And so these are all going to be atoms, but the opposite thing would be ions, when the positives don't equal the negatives, right? There is a charge. Okay? It's not going to apply necessarily here, but we're going to use it anyways. We're going to build on sample problem 2.4. Okay, so the top number, called the mass number. All the mass of the atom is located in the nucleus. So the protons and neutrons, that's what that is. And sometimes you might see something like this. Not shown in this problem because, well, the chemical symbol tells me the atomic number. Because if it has 14 protons, the number on the bottom is the atomic number of protons, then it has to be silicon. Okay? This number is the protons and neutrons. That's the number of protons from the periodic table because it's silicon. All right, so they all have the same number of protons because they're all silicon. If they had a different number of protons, then they wouldn't be silicon. And they have different numbers of neutrons because, well, they weigh different amounts. And the protons aren't changing because that would change the identity of the substance. So it's got to be the neutrons that change. And when I add these numbers up, I should get the top number. So those are the number of neutrons. And since these are atoms, which means they have a charge on them, they all end up with 14 electrons because the electrons and protons have to be the same to cancel each other out. Since protons are positive, right, protons positive, electrons are negative, when they're the same, they cancel it out. Now we're going to get a little crazy here, and we're going to add to the problem, and we're going to make it different. We're going to make these things in ions. So let's start off with the first one. Let's make silicon -4. Okay, what that means is, if it's a negative charge, ion, what it means is it has extra electrons, okay? Has extra electrons. Or, ready, another way to say it is more electrons than protons because, well, these are negative and these are positive. In order to be -4, I have to have more electrons, more negatives than positives. Now, I can't change the number of positives for silicon because if I do, I change what element I have. 14 protons defines what it is. The neutrons and electrons don't define it. It's only the protons. And we can see the neutrons don't because of these different isotopes. So what I have to do is I have to change the number of electrons. So if it was a -4, that would mean that I have 18 electrons. Negative, right? If we change the top number and made it a positive charge, a positive charged ion, we have extra protons, right? And so we would have less electrons than protons. We run into the same issue though, ready? Because we can't change the number of protons. We always have to change the number of electrons because number one, they're on the outside, and number two, they're small. So they're not in the nucleus, so they're not stuck together by a strong nuclear charge. They're just moving around the outside. So if it was positive, that means I'd have less electrons. So to make ions, right, I'm always adding or removing electrons. Okay? So that would be sample 2.3 expanded. Sorry, 2.4 expanded. All right. So the next one deals what we call a weighted average. This is going to be sample problem 2.5. Okay? And sample 2.5 we'll jump into a second, but we're going to talk about weighted average first. Weighted average first. And so weighted average means and everything's created equal. So let's look at your grade. 50% of your grade is based on first card marking, and 50% is based on second card marking. I want to keep it simple, so I'm going to say, okay, let's say you got your score, right, was a 90, first card marking, and 80, the second card marking. Well, if I wanted to get the average, you would just add the two of them up and divide by 2, because these two are equal, right? Only 2 of them. But there's another way to get it. You could take the 90 and multiply by 0.50, add it to 80 and multiply by 0.50, and you can get 85%. But adding them up, because they're weighted the same, and dividing by 2 would also work. But let's say I did something different. Let's say I made the card marking 40% for the first one, and then 60% for the second one, because I want to reward those people that maybe started slow, but then picked it up, okay? So then I would take that 90, instead of multiplying by 0.5, I'd multiply by 0.40. And I take that 60, I take that 80 and multiply by 0.60. And I add the two of them up. We'll do the math, ready? Clear, turn it on. 90 times 0.4 plus 80 times 0.6 equals 84. So 84%, right? So the grade dropped because I had more focus on the second semester. And they're not equally weighted, so I couldn't add them up and divide by 2. I'd get this. I got that number because this one was more important than that one. So it drew the average closer to it. This is a weighted average problem, a simple one. We do chemistry the same way. Example, problem 2.5, we're dealing with 2 isotopes of silver. Silver 107 and silver 109. Okay? Silver 107 exists 51.84% of the time. And then silver 109 exists 48.16%. Okay? Now, when I look at this, I can tell that if they were equal, then I'd just add the two of them up, and the average would be 108. If they're not equal, it pulls a little bit more towards the 107 than it does the 109. So the average should be below 108. Okay? Just a little bit of logic there. Now, let's give you the real values for this number. This is rounded. We'll give you the real number. We'll call it 106.90509. That's what we call the atomic mass of one silver 107 atom. And then the other one would be 108.90476. This number is that number rounded. Sorry, this number is that number rounded. Okay? So we're going to do it the same way as these. We're going to start with the actual number, 106.90509. I'm going to multiply by its percent. I'm going to divide by 100. And then 108.90476 multiplied by its percent. Okay, and when I add them up, I think I end up with like 107.87. Again, like I said before, it's a little bit closer to the 107 than it is the 109 because, well, it's a little bit more 107 than there is 109. And it's a weighted average problem. All right, so that was sample problem 2.5. Sample problem 2.6. Okay? Sample problem 2.6. It says for each of the following Z values, Z stands for atomic number. Give the name and symbol and group and period numbers of each one of them. Well, I don't know how much of this stuff we need to do. Let me see that really quick. I have a periodic table. Let's go through some of the finer points of the periodic table. Make our lives a little bit easier. Oh, we've got a nice glare going on there from the shininess. Okay. So this is the periodic table. And we kind of went through this in class, so I don't need to do a lot with it. But the big thing is, it's all lined up based on increasing atomic number and the number of valence electrons. These first two columns and these columns over here are usually pretty consistent with what we call their charge, because they have a consistent number of valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. These don't react to anything, so we don't really worry about them for now. Okay? The ones in the middle, there's some variance in there. They have something called d orbitals. They're kind of strange. So we're not going to worry about them yet. Okay, so let's look at the first one. It says atomic number 38. I can see that it's a metal. You know that metals are losers, right? So what Ba likes to do is lose 2 electrons. Because it has 2 and it's a loser, so it loses both of its valence electrons. Okay, so it forms a +2 charge. All right, and it's a metal. It's a main group metal, which means it has a consistent charge. I don't know what else I need to do with that stuff. All right, sample problem 2.7. Predict the monatomic. Mono means single ion formed by each of the following, and ion means has a charge. So we'll start with iodine over here. Okay, it's number 53, and it has 1, 2, 3, 4, 5, 6, 7 valence electrons. And we know that 8 in chemistry is the magic number, and we know that iodine is on this part of the table, which makes it a gainer, not a metal. So it likes to gain electrons. It likes to gain 1 electron to become like xenon. So a neutral atom has 53 protons and 53 electrons. But if I gain an electron, I still have 53 protons, but now I have 54 electrons. So iodine likes to form a -1 charge. Calcium, way over here, is just the exact opposite, right? Calcium is a metal, which makes it a loser. It doesn't like to gain electrons at all. But it still wants to get to the magic number, which is 8. So what its options are is, well, it can go ahead and lose 2 electrons and become like a noble gas. And it loses both of its valence electrons to do so. So calcium likes to be a +2. And then aluminum is over here. It's still a loser. It's a metal, right? And what it can do is gain all these to get to here, or lose these 3, and that's what it does. It loses 3. Aluminum is a +3. All right, the next step. It says name the ionic compound form, and this would be sample problem 2.8. Name the ionic compound form from each of the following pairs of elements. Okay, so we're just naming them. This is simple. So we have magnesium and nitrogen. So we'll call it magnesium and nitrogen. Okay, so these are all going to be metals and nonmetals in sample problem 2.8. which makes them what we call ionic. Okay? They're ionic. And we're going to keep them simple. We're going to call them main group metals. Okay? Which means they're going to behave consistently. So for example, on our chart, the main group metal is sodium. Sodium is always a +1. They're always +1s. Everything in group 1. Everything in group 2 is +2. Everything in group 3 is +3. Now I know cadmium is over here, but we're going to assume it behaves consistent like it's supposed to. Okay? We're going to make that assumption. It's a +2. And it'll do it. We'll explain later why. Okay. So it's going to be consistent. All right. So let's look at magnesium and nitrogen. We're going to write it. So when you name ionic, this is an easy one. You write the first one out like it is magnesium. It's got to be the metal first, the less electronegative one. And then nitrogen. The second one always gets a change. With a singular element, it always becomes IDE. So A would be magnesium nitride. B would be iodine and cadmium. Now cadmium is a little tricky, but we're going to assume it behaves like all the rest. So when we write the name of it, we should write cadmium first because it's a metal. You always write the metal first. And instead of writing iodine, we're going to write iodide. That lets us know that it's written second. And we always change the ending of the second element to IDE, whether it's an ionic compound like we have here, or what we call the molecular or covalent compound, which we'll talk about later. Okay? Strontium fluoride, so strontium and fluorine. Okay, and again, all we're changing is the IDE ending, so this would be C. And then D would be sulfur and cesium. So we'll just make it cesium. Change the ending on the second one because it's an element IDE, cesium sulfide. Okay? And those are the problems I think I worked out in class, right? I didn't think we went any farther with it. We will work farther soon. The next time I see you, we'll spend a ton of time on naming. Maybe have to spend a little more time than I wanted to. Okay? And that is it for the things I went through, the notes I went through